All right, recording started. Hello, everyone. Welcome to the last SPS seminar of the season. So, thank you very much for joining us. Today is my great pleasure to introduce you two speakers, actually, who will be presenting in a joint work in a joint manner. So, it's gonna be a fun day for us. This is new. So, first of all, let me introduce Edim Elmachtoub, who is joining us from Columbia University. He received his PhD from MIT ORC and his BS degree from Cornell ORIE before, and he's currently an associate professor of industrial engineering and operations research at Columbia, where he's also a member of the Data Science Institute. He's separately also serving as an Amazon scholar. And Adam's research spans two major themes. I'm sure like many of you in the audience are very familiar with it. First of which is designing machine learning and personalized methods to make informed decisions for industries, a lot of applications you can think of. The second stream you can see is the new model and algorithms for revenue and supply chain management, especially in modern e-commerce and service systems. I'm not going to go through the list. Adam has a lot of awards that testifies to his research contributions, and he's also elected as Forbes 30 under 30 in science, which is another big accomplishment. So joining us alongside with Adam is Haofang Zhang, who obtained his PhD in 2024 from the same Department of Industrial Engineering and Operations Research at Columbia. And Haofang is currently a researcher within the machine learning research team at Morgan Stanley in New York. And Haofang's academic research, especially his primary focus, has been on data-driven decision-making, sequential decision-making under uncertainty, simulation and quantification, Monte Carlo methods, and generative models. Among his academic works, he was, for instance, a finalist in the 2023 Informs George Nicholson Student Paper Competition. And currently at Morgan Stanley, from an applied research perspective, Haofang has been focusing on developing forecasting and decision-making models, especially for time series analysis. So today they prepared this interesting talk. So Adam, the floor is yours. Thank you so much.
Thank you so much for inviting us. This is a great honor. I've always been like a wannabe optimizer. I feel like this is like my first real optimization gig, so it's exciting. But because of that, I uh, um, I really wanted to make sure that we got the technical part and the interesting parts of the talk crisp and clear. So I brought Haofang here. He was my former PhD student and really a brains behind a lot of this work. So this work is really exploring three sort of algorithmic frameworks that we probably all have heard of in some way. And these are what we call estimate then optimize, integrated estimation optimization, and sample average approximation, SAA. And we're going to explain what these are in like several different ways, from starting soft and then getting more and more technical throughout the talk. So at some point we'll give you the exact technical details, so don't worry in the beginning. So next slide. So we're really going to discuss two papers here. The first one is under revision in OR. That'll be a bulk of the talk. And then the second one is appeared in AI Stats this year. Both of these papers are also with our co-author and Haofang's co-advisor, Henry Lam. The first one is also with my former PhD student, Yon Fan, and the second one is with my current PhD student, Hai Shang. So just to give you a sense, the first one is more about asymptotic results, and the second was more about finite sample results. We'll explain more later. Okay, next slide. So this talk is about data-driven optimization, fundamentally. And the idea, as you all know, is that often we're not given distributions, but we're given data, and we need to solve some stochastic optimization problem from this data. Okay, we're going to be focusing on objectives where the objective is fundamentally the expectation. And the only way we can access the distribution is through data. Okay, And sometimes we're going to have some contextual information that is useful for predicting the missing parameters of interest. Okay, so in the base setting, we're gonna sort of not think about contexts too much, but pretty much all of our results can extend to a contextual case where you have some features or context that can be used to make uh, that can help us estimate the unknown parameters. And this is sort of the more modern lens to think about data-driven optimization, where you have lots of side information or features or context. Another thing we're going to do is really going to think about nonlinear objectives in this body of work. Um, so some examples. So here's like 3 examples. So the news vendor problem, portfolio optimization, electricity scheduling. All of these problems are really going to fall into our framework. So um, the common feature of all these problems is that the objective is going to be nonlinear. So in news vendor, you have different costs for inventory versus holding, and you have this sort of classic um, setting where sometimes the backlogging is more expensive than the holding cost, but we and in this setting we need to predict the demand for the product. So if you predict the demand exactly, then you're able to get zero cost, but of course we cannot do that. And common constraints here would be like capacity constraints and things like that. And the context for forecasting or predicting demand are often like prices, weather, economic indicators, and so on. Okay. Another key component of all these problems is that, again, they're going to have not only a nonlinear objective, but often they have constraints. And the constraints make these problems quite challenging to think about when you have context. Portfolio optimization, there you often care about some combination of mean and risk of the portfolio, and risk is often measured by some kind of variance notion. So that's how we arrive at a nonlinear objective. What's missing here that we have to predict is the return of each asset. Okay, and you can use historical features or contexts like the returns, news, and other economic indicators. And here the constraints are often that the sum of the weights of the portfolio have to add up to 1, which is a simplex constraint. And briefly, like in electricity scheduling, you often have nonlinearities arising from the actual physics of the system or of the cost. Um, and you have constraints on, for example, like how you can turn on and off certain sources, or you can't make changes too rapidly, things like that. And you have to forecast some kind of energy prices or demand um, using context, such as past and future temperatures and historical demand and seasonality and things like that. Um, and just to um, make it clear again, the nonlinearity here matters because you may have heard like of predict then optimize frameworks. And here we're going to think about estimate then optimize because in the nonlinear setting, you really need to estimate an entire distribution to solve the problem properly. But with linear objectives, it's sufficient to just predict a single point prediction by the simple property of linearity of expectation. So I have work on the linear setting, and here we're really thinking about the nonlinear setting where point prediction is not sufficient, and you need to estimate then optimize, estimate an entire distribution. Okay, next slide. So diving in deeper, here are the 3 ways I think to go about these classes of problems. So the first one is SAA. Um, that's the first one probably that comes to mind for most of us, including me. So you're given a bunch of data, samples of the unknown parameters in your objective, and you simply formulate an SAA problem and solve it. Um, good. The next one is what we're calling estimate then optimize. And here what we mean is we first going to estimate a distribution from the data and then solve the stochastic optimization problem. Okay, so rather than just plugging in the data directly, you're going to formulate, you're going to fit some distribution, maybe like a Gaussian or something else, and then try to solve the pure stochastic optimization problem directly. How you solve that We're not going to really get into details, but maybe you end up sampling from that distribution anyways. Okay, but the idea is like we're fitting some parametric distribution. And the third one, which is the interesting one here, is integrated estimation optimization. And here what we mean is that we're going to still fit a parametric distribution to the data, but the way we fit it is going to be in a way such that we're going to find the best fit that works for the downstream optimization problem. So when we're fitting the parametric distribution, we're going to take into account the optimization problem in the estimation itself. Okay. In contrast to regular estimate and optimize, where you just estimate the distribution using a standard approach like maximum likelihood estimation. And so the fundamental topics of this research are how do we compare these three approaches? And we want to think about like a principled framework to statistically compare these approaches, both in like large sample regimes and finite sample regimes. Okay. Um, so hopefully the idea of the research is clear. Now let me like formalize one specific use case we're going to come back to multiple times through the talk. So we'll specifically dive in on the news vendor problem, just make sure and start introducing gently the notation. So here in the news vendor problem, we'll let W denote the number of units we want to order. And the unknown demand is represented by the parameter Z. Okay, so if it turns out that the demand is less than the amount we ordered, we're going to pay holding costs, represented by the parameter H. And you pay holding costs on the extra amount you ordered. If you didn't order enough, or the demand is more than you ordered, then you back order it. And the parameter here is B. And typically B is like a lot bigger than H. Okay, so the total cost is the combined holding costs and backlogging costs, and only one of these is going to be positive on a realized demand scenario. Okay, so remember Z is random, so Z is coming from some distribution P, which we're not necessarily going to know, but if you did know it, you would solve this problem here to get the news vendor quantile. Okay, and remember the optimal solution to the news vendor is like in closed form, it's like the B over B plus H quantile of the distribution. Okay, but we're not going to have access to the distribution P. We're only going to observe samples from it. Okay, so the data-driven optimization problem is generally going to be framed like this. So we want to find an optimal solution W star to minimize some expected cost. So this cost function is nonlinear. And W again is a decision variable. Z is the random variable. And Z is coming from P, which is an unknown data distribution. Okay, and going back to our news vendor case, here the cost was simply the news vendor cost. Okay. So you can see it's nonlinear because we only take the positive components of these under and over ordering quantities. Again, W star is going to be the true optimal solution that we're interested in. And we'll let Zn, Z2, and Zn denote the n samples of data we're going to be provided to solve this problem. Again, we don't get to CP, but we're going to assume that these n samples are going to be IID samples from P. And so that's the sort of base case version of the problem that has been like very well studied. And more recently, people are thinking about adding context to this stochastic problem, optimization problem. So sometimes it's called contextual stochastic optimization. And the idea now is that I'm given some features X, and these features sort of directly are help me predict Z. So now Z is dependent on X. Okay. So the randomness in Z again is affected by X, and so Z is now coming from the conditional distribution of P Z given X, which we're not going to know. Okay, C is still nonlinear, and we might also have some constraints. And actually, in a lot of our problems, of course, you're going to have very constraints, and that makes this more challenging. So G is going to denote the constraints, and capital J is the number of constraints. So now the data looks slightly different because now we're still observing n samples, but we also get to observe the features along with each sample. So we observe x1, z1, x2, z2 up to xn, zn, and this is all coming from the joint distribution. So circling back to the news vendor problem, this is the multi-product news vendor where we have p different products and z1, zp represents the randomness for each of the p products. And we can tie these p products together. We're going to have through a capacity constraint. So you might say that the total ordering quantity from 1 to p is capital C. And you might be able to sort of use context here because you might have like weather or economic indicators to help us predict the demand for each of these products. So this would be like a constrained contextual stochastic optimization problem. Okay, so keep going, how fun. So this talk is directly about solving these data-driven optimization problems. Again, generally P is not known in practice. And what we're going to do is consider solving it directly using SAA and the empirical distribution. And we're going to consider solving it with a parametric approach where we going to fit a distribution to the best fit possible in a family of distributions. So like the class of Gaussian distributions, for example. And we're going to choose these parameters um, um, either through the classical approach or an integrated approach. And for convenience, we're going to define this W theta as the best decision for the under the distribution P theta. Okay, so if I instantiate a single distribution with some parameter theta, and then I solve this contextual stochastic optimization problem, that solution, we're going to call it W theta. And what's, I think, interesting is that we're going to compare this parametric and non-parametric approaches uh, together. All right, so now, next slide. So bringing everything together, we're going to show you all three approaches now using the mathematical notation, and feel free to ask questions at the end of this slide to make sure everyone understands. And for right now, this is the setting where there's no context and no constraints. Okay, so SAA looks like this. This optimal solution with SAA is basically you just plug in the data directly, and this is like using the empirical distribution. So you're minimizing the average cost over n samples of C, W, comma, Zi. So Zi is the realized parameter in sample I. Okay, so in news vendor, Zi would be the actual demand. Okay, but the key is that W, it doesn't depend on I. So you're making one decision that works best on average across all the samples. In the ETO approach, estimate then optimize, we first have to estimate theta and find the best theta in the family of distributions P. Okay, so this is a predetermined hypothesis class or family of distributions of which we need to fit the best parameter. Then given the parameter theta, we're going to solve the stochastic optimization with P theta, and that solution is called W theta. Okay, and we're going to consider two different ways to fit that parameter theta. The first way is the classical approach, MLE, maximum likelihood estimation. Okay, so to do this, you typically take the log likelihood. So here we're calling theta ETO as the argmax of the average log of the log likelihood, basically. Okay, and once you find this MLE fitted parameter theta, you plug it in. So the solution from the ETO approach is you solve the stochastic optimization problem with P theta ETO, and that's WETO. And then the integrated approach is that rather than using MLE, we're actually going to minimize the average cost with the best possible theta. So you try to minimize the cost. It's not exactly empirical cost. It's like the solution I would have implemented with theta applied to the realized samples. So it's summing over 1 to n C W theta, which is the solution I would get from using theta, and observing the cost on sample ZI. So I'm trying to minimize the downstream decision error with my choice of theta here. And we're going to call this solution WIEO. Okay. And now I want to pause for a minute or two to let you ask questions. And also just think about like which of these three approaches actually yields the best performance. These are all reasonable ways to think about the problem. And if you have any thoughts yourself, feel free to share them now or ask any questions.
Yeah, hi, this is Alan King. So W theta, I guess, will you go on to talk about reasonable parameterizations of W theta, or is this just going to be some empirical?
So we're going to assume we're given the hypothesis class of distributions you're interested in fitting.
Gotcha. Okay.
So like the hypothesis class is given, and you just want to pick which specific parameters you want to. So it could be like you want to pick the mean and variance of Gaussian distributions. So you still have to estimate those parameters. But the class of Gaussian distributions is given, let's say.
Thank you.
Adam?
Please.
Hi. Yeah, just to clarify, so then when you solve the second and third problem, I assume you're still gonna need some sampling method, right? Or do you assume that you can solve it some other way, getting once you find the theta, you get a distribution with this parameter theta, but then you still have a problem with a continuous distribution to solve, right? Do you apply
Yes.
sampling there to solve the problems 2 and 3?
Thank you for the question. So indeed, so how you solve the problem with P theta, we're not addressing that here. So solve it however you want to solve it. In practice, probably you're going to use some Monte Carlo sampling from the distribution. So we're just going to assume though that you could solve it pretty much within some provable, we're allowed to solve it with some small error, and Haofeng might discuss that later, but we're not going to address the computational issues here. Only going to talk about the statistical values between these three methods. Yeah.
Okay, thank you.
Okay, good. So now I'm going to pass it to Haofeng, who's going to dive deeper and then share all the interesting results.
So let me first show how these three approaches apply to the standard single product use random problem. Suppose now P is known, then it is well known that the optimal solution will be B divided by B plus H quantile of the distribution of P. If P is not known, then the solution using our previous three approaches would be the following. The SAA solution will be B divided by B plus H quantile of the empirical distribution. The ETO solution will be, again, some quantile of the distribution estimated by the MLE. So the IO solution will be the quantile of the distribution P theta IO, where theta IO is the parameter minimizing the empirical average cost. So the difference between these three approaches is essentially how we choose to estimate the distribution P. So I want to emphasize that In this single example, we can get the exact closed form solution. However, for our theory, we do not really need to know any information about those closed form solution. Okay. So let me discuss the extension of the previous approaches to contextual optimization. I highlight the difference in red. First, we extend the SAA approach. So in SAA, it will proceed as follows. The decision W is now a function of X that minimizes the empirical average cost. Now suppose we can see that any function that is defined only at the data xi by the value minimizing CWZI, then this kind of function will always be optimal regardless of how we define values out of xi. So this yield infinite number of optimal solutions, which means SAA overfits the finite sample problems and generalization issue arises. The feasibility issue may also arise if we have some constraint on W. So we do not consider the comparison of this exact SAA in the contextual problems. As for the other two approaches, the parametric approach is really very similar to the standard case. Here, the distribution P theta is now used to parameterize the conditional distribution PZ given X. The oracle problem now output W theta as a function of X. Since the conditional distribution differs at different X, we are now, so this W theta will now be a function of X. Okay. Here we are still interested in finding a good theta in this oracle. And as for ETO and IEO, so using this parametric idea, ETO and IEO can be naturally extended. So they still estimate the theta in the oracle, but from two different perspectives. The only difference is that now xi appear in the estimation step. So the output is now a context to decision map. Okay. So let's dig into some technical details. To evaluate the performance of a solution, we use the following criteria. The regret or the optimality gap of a decision W is the difference between the ground truth expected cost of W and the W stop. Obviously, the lower the regret is, the better the decision is. Because data-driven solutions are random depending on data, the regret of data-driven solutions are also random. Hence, we need a way to compare those two different regret distributions. One way is to just compare the mean, which is indeed used in some previous work. Here, we are able to do something better. We use a type of stochastic ordering called first-order stochastic dominance to compare the entire distribution. We say that X is first-order stochastically dominated by Y if any tail probability of X is less than the tail probability of Y. Importantly, this definition is equivalent to the property that for any increasing function phi, the expectation of phi X is less than the expectation of phi Y. When X and Y are both non-negative, which is true because regret is always greater than 0. It implies that any moment of X is less than the moment of Y. Therefore, this is a very strong comparison. So the goal of this work is to compare the regret of the three solutions from SAA, ETO, and IEO in both, not only large sample, but also finite sample environments. And our results can be summarized as follows. So in the asymptotic region, SAA has the smallest, in the misspecified case, meaning P is not in the parametric family P theta, then SAA has the smallest regret and ETO has the largest regret, asymptotically in the first order stochastic dominant sense. Interestingly, in a well-specified case, meaning that P is indeed in the parametric family P theta, then the performance ordering among the three approaches is completely reversed. I will describe these results more rigorously in the next slides. But right now, let's just look at some simple numerical results for the multi-product use vendor problem. So this figure shows the results in unconstrained, constrained, and contextual use vendor problem. We observe that in all experiments, ETO achieved the smallest regret in the well-specified case, but it has the largest regret in the misspecified case. This is consistent with our theory. Although our theoretical results are in the asymptotic sense, our experiment also shows that the same trends also holds in the reasonable finite sample region. Therefore, we will also develop some results in the finite sample region. Okay. So let's discuss some previous literature. So recently, there have been a number of papers that propose various approaches for data-driven optimization, such as the SPO framework for contextual linear optimization and conditional IO framework for contextual nonlinear optimization with discrete distribution. However, most of the research here mainly focus on developing the algorithm or demonstrating their general effectiveness. As different papers adopt different settings, direct statistical comparisons among different approaches are not fully clear. To our knowledge, there are 3 studies that are related to us. The first paper here compares ETO against IO for contextual linear optimization, where the expected cost can be separated into the decision and the mean response of the context. However, as Adam discussed previously, so this property does not really hold for nonlinear optimization. This is a fundamental difference between contextual linear optimization and contextual nonlinear optimization. The second paper shows that SAA achieved the smallest regret asymptotically compared with distributionally robust optimization approaches in the sense of second-order stochastic dominance. However, this paper focuses on non-contextual optimization, and it does not involve the detailed comparison among the covariance matrix appearing in our non-parametric and parametric approaches. The third paper here is about operational statistics or operational data analytics, so which has a similar spirit to the IO approach. They consider specific optimization problems instead of our general problem, and their method is in a small sample region. So next, I will discuss our main theorems in more details. So the first theorem says that when a model is misspecified, as n goes to infinity, the regret of SAA converges to the minimum value 0. And ETO, the regret of ETO will converge to a value that is larger than the one that IO converges. So this theory is relatively easy to see because SAA is the best because there's no model misspecification in SAA. It has 0 regret asymptotically. On the other hand, by the construction, IEO will ultimately identify a theta that has the minimum expected cost among all the parameters. Therefore, it should be at least as good as the one found by ETO. So we also remark that this inequality is not a strict inequality. It's possible that some of them are equal. So the second one is about well-specified case. So interestingly, our previous findings completely reversed when the model is well-specified. Okay, so this theorem shows that under some mild assumptions, such as the first order and second order optimality conditions, the asymptotic regrets of all 3 approaches are 0, and they all converge at the rate 1/n. Therefore, we cannot distinguish them based on the first point 1. So the second point says that the asymptotic behavior of n times regret are different from each other. In fact, n times the regret converge to a certain limiting distribution for all 3 approaches, called GETO, GIO, and GSAA. They have the following relation. So GETO is first order stochastically dominated by GIO, and GIO is first order stochastically dominated by GSAA. Okay. So with additional efforts, this result also hold in the constraint optimization and the contextual optimization, but to highlight our ideas, we will mainly talk about them in the standard case, in the non-contextual, non-constraint case. Okay. So any questions for now? So let's look at some numerical results. So in this figure, we specifically look at the well-specified case and check the stochastic dominance given by our theorem. So this figure shows that shows some tail probabilities and some moments of n times regret for the Luce-Van Der problem. It confirms that the regret indeed converges at the rate 1 over n, and the stochastic dominance relation holds, as our theory indicates. So let me discuss our previous theory a little bit. So first, our results provide a relatively strong comparison among the three approaches in the first order stochastic dominance sense. So it implies the relation on any moment, including the mean, and in fact is even stronger than any moment comparison. Second, so since the integrated approach has demonstrated its empirical power in many recent research, our result seems to provide an opposite view to the common belief, showing that ETO could be better than IEO in some cases. But we caution that this finding holds asymptotically in a well-specified model. In other words, when our model is sufficiently good and we have sufficiently many data, then there is no need to use So this sounds reasonable, right? So however, in practice, this ideal situation seems to be too restrictive. It could be very hard in practice to construct a well-specified model, and sometimes the model simply cannot be rich enough to be well-specified. Then our first theorem shows that IEO is better than ETO. This might explain why IEO is likely to perform well in practice, but how much better? We will address this in the next theorem. So this theorem provides the higher order expansion of the regret, regardless of the model specification. So it generalized the previous result. Again, when we look at the zeroth order regret, that is the asymptotic distribution of the regret, then SAA and IEO are better than ETO. I have already shown this result previously. Let's move one step further. When we look at the first order regret, that means we look at the asymptotic distribution of square root n times regret, then SAA and IEO are still better than ETO, as they don't even have this first order regret because they converge to zero. So this shows that when we look at the zeroth order and first order term, we observe a universal ordering among three approaches. Now, let's dig into the second order term. We look at the asymptotic distribution of n times regret. If the model is not well specified, then there is no universal ordering. Okay. So let's interpret this result. So this result shows that IEO has a universal double benefit compared to ETO. That means IEO is always better in the first two dominating terms, the O1 term and the O1 over square root n term, regardless of the model specification. Moreover, compared with ETO, IEO has an additional benefit. So it has a lower asymptotic regret and a faster convergence rate because, as we can see previously, so the first order regret of IEO is 0. That means IEO minus the model bias will converge at the rate 1 over n. However, for ETO, even if we subtract the model bias in ETO, it still converge at the rate 1 over square root n. So that means IEO has a faster convergence rate. Second, IEO can be worse than ETO only when we look at the second order term and then the model is well specified. That means IEO, so ETO, the benefit of ETO only appears in the second order term. So it's going to be smaller than the effect in the first order and the zeroth order term. Finally, the previous results are all in the asymptotic sense as when the sample size n goes to infinity. But we have already observed the same trend in experiments. So a natural direction for us is to develop finite sample results. Okay. So, however, the deriving finite sample results is typically not an easy task. A standard routine for finite sample performance is to derive generalization bounds, which are typically upper bounds. The question is comparing upper bounds meaningful? If the upper bounds of IEO, let's say if the upper bound of IEO is less than ETO, it does not necessarily mean that IEO itself is better than ETO. Therefore, we develop a new path to analyze finite sample performance that consists of both upper and lower bounds. The key concept of our approach is to convert so-called Berry-Essing type bounds for the estimation error to finite sample bounds for the decision error. Okay, so the finite sample analysis is more delicate than asymptotic analysis as it requires a new ingredient in our analysis. We need additional efforts to characterize and measure the degree of model misspecification. So this is new in the finite sample analysis because if in an asymptotic case, if the model is misspecified, regardless how small it is, when n goes to infinity, this will be huge. So yeah, that's the key difference. We need to, in the finite sample case, we need to balance n and the degree of model misspecification. So this is our theorem for finite sample comparisons. So I want to highlight that this result here holds for any sample size n, including 1. So the first part is Berry-Essing type bounds that directly shows the difference between n times regret and its limiting distribution G. As we already know from our previous theorem, when n goes to infinity, the difference will be 0. But here it gives you the difference for any finite sample. So unlike generalization bound, this bound consists of both upper bound and the lower bound for the regret. This is critical for comparison on the exact regret value. Okay. So we can also get the same results for ETO, which I omit here. So the second part of the theorem says that when the model is nearly well specified, you can still claim ETO is better than IEO, but with a tolerance epsilon nt that is related to the estimation error. The third part says that when the model is a bit more misspecified, we can claim IEO is better in terms of the tail probability. Here, CT is a positive constant that depends on T, but not N. So all these results are consistent with our previous asymptotic results when N is sufficiently large, but this one provides a more refined finite sample guarantee. So our results shows that in the finite sample region, there is a performance transition when moving from a well-specified model to a misspecified model, characterized by the degree of model misspecification. And this can also be verified in experiments. So in this figure, we study performance change with respect to the model misspecification. So when gamma is equal to 1, which means the model is perfectly well specified, then ETO is better. But when we gradually reduce gamma, meaning that we increase the degree of model misspecification, then ETO becomes worse. When gamma is about 0.9938, ETO and IEO perform almost the same, but when gamma is small, IEO becomes better. Therefore, we observe that even a small misspecification can result in a better performance of IEO. This is related to the double benefit of IO I discussed previously. When we have a small model misspecification, and the first two dominating terms in the regret becomes dominating. So the advantage of IO become distinct. So finally, let me give some idea on how to prove one of our main theorems. So the well-specified case. Recall that when the model is well-specified, the asymptotic regret is 0 for all approaches, which cannot be used to distinguish their performance. Therefore, we need to compare the behavior of the asymptotic n times regret. So roughly speaking, the proof consists of the following 3 steps. In first step, we derived the closed form limiting distribution of the regret by using the second order delta method using the first order and second order optimality conditions. The resulting G roughly behave like a quadratic form of the limiting distribution of the parameters or decisions, which is a Gaussian distribution by standard M estimation. So the matrix in the middle involves the Hessian information from the expected cost. In step 2, to compare G using stochastic dominance, we use a technique that can convert the stochastic dominance comparison to the covariance matrix comparison. So leveraging this technique, it is sufficient for us to compare the covariance matrices in the Gaussian distribution of SAA, IO, and ETO. And these techniques requires H to be positive semi-definite, which naturally holds by the second order optimality conditions. So basically, step 1 and step 2 here provide a systematic framework that can convert inference error in statistics to decision error in decision making. Now, in step 3, to compare ETO and IO, we leverage the idea in a multivariate Cramer-Rao bound. So essentially, Cramer-Rao bound says that MLE achieves the smallest asymptotic covariance, which is the inverse feature information. However, we need a twist here because we are now interested in the decision performance instead of the statistical performance, estimation performance. We do not apply Cramer-Rao bound directly on MLE, but on the gradient of our objective function. So to compare IO and SAA, we need something more. So intuitively speaking, SAA allows W to be any point in the decision set, where IO restricts W to be a correct subspace induced by theta using the oracle problem. So this subset is correct because the model is well specified. Therefore, IO is like the restriction or projection of SAA in the correct subset of W theta. And thus it has a smaller covariance than SAA does. So the rigorous proof requires building a new matrix inequality using this projection idea, which is just like this. So interestingly, this new technique allows us to compare the non-parametric approach SAA with the parametric approach IO. Oh, okay, so I want to make a final remark that our results also hold in the constraint case. Suppose now we have some lower inequality and the inequality constraint on the decision W, where the objective function is the same. To handle this problem as a standard routine, we introduce the Lagrangian function for SAA and the oracle problems in IO and ETO. Now we assume the constrained version of first order and second order optimality condition, particularly the KKT condition. Then our previous finding still holds in this case. However, I want to emphasize that the proof is much more difficult here. So constraints introduce many additional technical difficulties. For instance, we need to handle the Lagrangian function under the constrained optimality conditions. And the Hessian of the Lagrangian function is not positive semi-definite anymore. So our previous lemma would not hold anymore. Moreover, more Penrose pseudo-inverse appears in the covariance of SAA, but it is well known that the pseudo-inverse matrix does not really have the continuity property. So we cannot directly transfer our previous matrix inequality result to the constraint case. So to conclude, in this work, we create a principled framework to statistically compare different approaches, asymptotically in a strong sense of first-order stochastic domains of the regret. And we also provide some finite sample results. Our results are the first in a nonlinear objective setting. In the future, we are interested in some directions, such as studying procedure that can address the distributional shift or uncertainty in the data, or to compare other data-driven procedures, such as long parametric approach or generative models. Okay, yeah. Any questions?
Thank you very much.